Okay, so next topic, we just talked about the common fork join pool. I'm going to show you how to program against it, which is kind of fun, or program with it, not against it, with it. And we're going to look at a fun example here that illustrates how this can be done. So first of all, the fork join pool is typically best used for programs that don't really match the parallel streams model. And the parallel streams model really likes things that divide and conquer evenly. So if you've got something where you've got input that can be divided and conquered and split, that works well with parallel streams. But not everything works that way. And this particular example is a variation of the one shown at this article here. And this article illustrates how we're going to count certain things in a recursive folder structure. So this program is going to count all the files that are reachable from a root folder in a recursive folder structure. And it's also going to keep track of how large all the content was there as well. And you can get that here at this link. So what we're going to do, and we're going to look at this in more detail in a second and run the program, we're going to start out by creating a new array list, which is going to be a list of fork join tasks that return long. We'll see what that means in a second. We call those forks. You'll see why we call them forks in a second. And then we're going to take each file within the current directory structure. So if you think about a recursive directory hierarchy in Windows or Mac OS or Linux, you've got some root, and then within that rooted file system, you will have either some files and or subfolders within that. And those subfolders may have files and subfolders and so on and so forth. And so what we do here is we take every one of the files, and a file could either be a folder or a document, and we go ahead and we create a new object called a file counter task, and we pass in the file and then a couple of atomic objects that keep track of how many documents and how many files we've seen. And we then go ahead and fork this. So for every file in our list of files, we're going to go ahead and create a new fork join task called a file counter task and fork it. And what fork does is it arranges to run this object in the context of, in this case, the common fork join pool. And you'll see that when we look at the actual program. So all these things are going to be basically partitioned out to threads in the common fork join pool. They will then all go run in parallel. And then when we're done, when all those things are done, this code runs, and it basically goes through the list of fork join tasks, and it calls task join on each of them, and it will count up the results. And what we get at the end is a count of the number of files, which could be documents or folders, reachable from some root folder in a recursive directory structure. So that's what that's doing. And this works nicely because there's no guarantee that you're going to have an even number of things that can be split using the underlying, or the parallel streams framework. So we're now in the folder in my IntelliJ project that deals with, start again. We're now in my IntelliJ project for the fork join example. And we're going to take a look at how to count the number of files and get the size of the files using the fork join framework. And here's the main program that's going to do all this stuff. As you can see, the first thing we're going to do is we're going to warm up the thread pool. And then we're going to go ahead and run this program called run file counter task, which is going to illustrate the fork join framework. There's some other examples here too, which we're not going to talk much about right now, but are pretty cool. We can talk about later. So what this does is this goes ahead and runs a test, and it's going to run this in a new fork join pool. And in fact, what we really want to do here is we want to say fork join pool, common pool. So this will now run in the common fork join pool. And we're going to give it an entry point, which is called file counter task. And that's going to be given a new file that points to the root of a very large recursively structured file hierarchy that contains lots of source code I've written over the years for the purposes of demonstrating Java features. And we're going to go through and take a look at how many files and directories and so on are in here, and how many documents and directories. And we're going to give the name of the program, and we're going to say we want to print the statistics. So let's go ahead and run the test here. If you look at the test, what the test is going to do is it's going to garbage collect everything first. If the name of the test is warm-up, we're going to skip that. We don't want to record the warm-up, we do. And then what we're going to do is we're going to go ahead and run the test, except we're going to run the test timing it. So this is my little time helper class that takes a snapshot of the time at the beginning and the end, and then it's going to record that into an internal hash map under the name of the test. The way we're going to run this is we're going to take the parameter that's passed in, which is a fork join pool, which in this case, as we saw before, was the common fork join pool. So we pass the common fork join pool here into that. And then we're going to go ahead and say fork join pool invoke. And invoke is a method in the fork join pool that will do a two-way synchronous call, which will not return until all the parallel processing is done. And it's going to give back the number of bytes of all the processing that it took. And so we pass in the test task, which is what's passed here, which defaults to the root of this giant hierarchy of files and folders that we have down there, or documents and folders. OK, so it's going to go ahead and run that. So let's take a look at what we're going to run. And what we're going to run here is file counter task. So as you can see, file counter task is going to extend abstract file counter. Abstract file counter is just a little helper class that is going to be implemented here. And it keeps track of the file we're looking at, keeps track of the number of documents we've seen so far, the number of folders we've seen so far, and then it's also got a couple of other helper methods that just return some information that we might need during our traversal. Here's where things get interesting. Here's file counter task. We take the current file and the atomic longs we just talked about. We give them to the superclass, to the abstract file counter. And then we have a method called compute. And compute is something that comes from the fact that abstract file counter extends recursive long. So recursive long is a helper class that's defined as part of the fork join pool framework. And it's going to be parameterized by the type that we're returning, which is a count, which is a long. So there's a method defined in recursive task called compute. And so we're going to go ahead and take a look at the compute method. Here's the compute method. This is overridden from the method that's provided in recursive task. And here's what it does. We check to see if the current item we're looking at is a file. If it's a file, we're going to increment the document count. By the way, file is kind of a funny name. I should say if the entry is a file, not if a file is a file. If the entry is a file, we will then go ahead and increment the count of documents and return the length in bytes of the size of that document. Otherwise, we've got ourselves a folder or directory, or subfolder or subdirectory. So we increment the folder count by 1. And then we're going to do that little magic we had taken a look at earlier in the slides. So we go ahead and get a list of the files or the entries at the current entry in the folder, which gives us a for each loop with a bunch of files. We don't know at this point whether the file is a document or a folder. And then we're going to go ahead and create a new file counter task, passing in the file that we're looking at, the document count, and the folder count. And we're going to fork that, which arranges to run it in the background in the common fork join pool. And then we're going to add that to the forks list, the list of fork join tasks. So we do that for every file. And keep in mind that file counter task itself will recursively traverse from that point if what we give it as an input, as the file, is a folder. So it'll keep doing this recursively as it goes down the hierarchy. And so all those things are now going to be up and running. And then the calling thread, the thread that did all the forking, is now going to go through a loop waiting for all the results to finish. And the way it does that is it calls the join method on each of these tasks. And that will block, logically block, doesn't actually physically block. It'll logically block and we'll wait until this particular task's result is done, in which case we get the sum and we add it to the sum here. And that will be tallied up for each of these things. And when all the processing is finished, all the joins will complete, and then we'll return the sum as the result, as the count of the number of elements that we found that were either documents or folders. So just for kicks, if we run this particular program, there's a bunch of other examples here which we're not going to talk about right now because that's a topic for another day. But you can see we started up, and it's going to go ahead and first start up by warming up the thread pool, and then it's going to run the results. And you can see that for the results we get back, we had basically 1,104 documents and 763 folders. So it's a pretty nice recursively defined structure. And each of the different programs gets the same results, which is good because that's what we'd expect. Otherwise, there's a bug. And then you can see which ones executed the best. And the file counter task we just looked at runs the best. And there's some other ones in there as well. We'll take a look at those at some other point. But anyway, that just shows you by using parallel processing, we can make things work pretty efficiently using the common fork join task. Now, the key thing to keep in mind in the back of your head, however, is that we had to keep track of a lot of details in this implementation. We had to keep track of this list. We had to initialize this forks list. We had to call ourselves recursively and fork each time and add that to the list. We had to go through the list of fork tasks and join them all. And had we used parallel streams, we would have been able to do very little. We would have very little to do. We would just write the parallel stream syntax, which is much more concise and clean. And so the question is, which would perform better? So we'll do a test of that at some other point later as well.